Good morning all. I've been taking another look at the 8-bit breadboard computer. So all it consists of here at the moment is just a free running oscillator. That's a 555 timer. There's a little 8-bit counter here. It's a very simple 8-stage ripple counter, but it gives me 8 address lines, which I'm using to address this RAM. This is a 2K CMOS static RAM. 16K bits, 2K bytes. And you can see the address here counting up on the 8 address lines. Now the 8 data lines from the RAM, of course the RAM contains nonsense garbage data because I've just switched it on. The 8 data lines are coming up to this switch bank, which I can use to write to this RAM. This is the write switch here. And you can see that at each address there is just garbage data. Well, it's not quite garbage, but it's just the random, well, it's not random, it's the pattern that is in the RAM when you first apply power. So today I'm going to do something a little bit drastic. I'm actually going to remove the program counter. So this computer is not going to have a program counter at all. It's actually going to have a latch. Well, let's do that right now, shall we? Let's just pull all these wires out. So there we have an address on the address lines. It's probably, well, it's floating, isn't it? So it's going to be floating around. The program counter chip, this isn't actually a program counter as such. It's just a counter. If it were the program counter, it would need to be able to be written to, and this chip can't be written to. So let's remove this chip as well. And look at the chip that I'm going to put in its place, and it's this. It's the 74LS273, and here is an LS273. Right, let's remove a few of these links because I don't want to put the chip in and have pins linked to ground and VCC, which really shouldn't be linked to ground and VCC. I'll put it in biased fairly well to the right. Actually, I'll go one more. Let's put it in there. Okay, so now I need to wire this latch up to make this new concept work. But perhaps what I should do first is explain why I've ripped the program counter out and I'm replacing it with a latch. So here it is. On my first build of the 8-bit computer, John Meacham left this comment. Were you inspired by Lorentz computing at 60 Hertz article? Well, I wasn't because I hadn't seen it, but I certainly have now, and I've said here, yes, I like the idea of not having a program counter. That's got me thinking. Thanks, John. So yes, thanks very much, John. So now let's take a look at Jeff Laughton's computing at 60 Hertz article. And this is it, Lawton Electronics, 1-bit computing at 60 Hertz. This page describes a tiny computer made from an EEPROM and a few logic chips. And if we scroll down to the circuit diagram, you can see the 2716 EEPROM here. Now that is actually the same size as my RAM. It's a 2K byte EEPROM because my RAM is a 6116, so it's a very similar number. And you can see here that what Jeff has done is he's taken the data outputs of the EEPROM, put them into this latch, a 74C374, and then taken the latch outputs and put them all the way back in to address lines, not the bottom 8 address lines, but that doesn't matter terribly. It doesn't really matter which address lines you use, but back into the address lines of the EEPROM. So actually, on the outputs of the EEPROM, you have a data value which provides the next address, the address when this latch is clocked. And the clock for this latch comes from just an oscillator. Now this will probably only start to make sense once I've wired this up. You'll notice I'm using an LS273, not a 374, and that's because this latch doesn't have tri-state outputs. We don't need tri-state outputs, but it does have a clear input, and I thought that was very important for getting back to program location 0. So I'll be wiring a switch onto that clear input, but for the moment what I want to do is get the Q outputs of the LS273 wired across to the address inputs of my RAM chip here. I think probably what I'll do is switch the power off at this stage so I don't blow anything up. Now it doesn't really matter which of these numbers I use as latch 0. In fact, because address line 0 is over here on the right, and I think all these wires are cut the same length, I will renumber these. So 4 can be Q0, 5 can be Q1, because these ones are nearest the right hand side. Then the next Q is here, so that can be 2, 3, 4, 5, 6, and 7. And then I'll use the corresponding D inputs to link round to these data lines, which I think are least significant bit here. Yeah, because that wire goes over to the far right hand side. That's the least significant bit on the data switches, which are used to program this chip. So let's get 8 wires in according to this arrangement to drive the address lines, and then we'll feed the inputs of this latch from the 8 data pins coming out of the CMOS RAM. Right, so that's 0, 1 can go over to there. 2 now jumps across to that point there, so let's pick up address 2, that goes there. And then 3 will go up there. That's what I've marked as 3, and so on. Oh right, I just realised I got 4 and 5 the wrong way around. You probably spotted that already, but it's fairly obvious. 1, 3, 5, 7, 0, 2, 4, 6. So they're now the right way around. Let's just do wires number 6, which goes to what is marked 1Q, so that's there. Wire number 7 on address pin 7 goes up to there. Now clock is over here on pin 11, so the clock from the 555 will need to jump right across to that top corner pin, and then clear is on pin 1, so I'll need to wire another one of these little PCB switches here to pull that down to ground and have a 10k or so pull up in order to hold that normally high so that we're not normally clearing the chip. Right, VCC goes there to pin 20. If I can get that one to fit in there. Another link for ground, which goes to pin 10. So ground to there. I put the switch in, but I'll need to just link links across and put a 10k resistor pulling up to 5 volts. Actually, I might be able to put that on the 5 volts down here, this red line down here. So let's get that wired up. Right, that's pin 1 pulled up, and then the switch to ground when you press it. The only other thing I need now is pin 11, which is the clock going to the output of the 555. So that should be it. So the clock should be clocking the latch. I should be able to clear the latch. The latch outputs go to the this display, to the address inputs of the RAM. Let's see if that works. I should get a random address when I switch on, and it's all high. The inputs of the latch are, yes, this is a TTL 74LS273, so I think inputs drift high. So it's reading all ones in, and of course it's being clocked continuously by this clock. So if I clear it, I can get it to go to all zeros on the address, and we get a different data pattern for that address. Of course, if I let go of that, the clocking just clocks in all these high inputs, so it immediately goes back to high. So now what I need to do is get all the inputs of this LS273 wired to the data outputs of my RAM chip. Right, so let's cut one at 9 centimeters and see whether that's long enough, and then if it is, I'll just do 8 pieces of wire all at 9 centimeters and just shove them in. Right, so I think I need a couple more at 9 centimeters, and then because I'm working my way towards the left of this chip, I think I'm going to have to go to 10 centimeters. So I've done 0, 1, 2 is that data line there, and the input is where is it? D for 2 is there. Okay, Right, last one, 7, data output 7 on the RAM goes to input 7, which is what was called 8D, which is pin 18. Shove that in there. Right, now we can see that something is happening. It's not counting, it just seems to be oscillating between two different values. But what we need to do is reset this to address 0. Okay, that's still oscillating between different values. So now to program this, I'll need to go into single step. So let's stop that. Let's go to address 0. Now, when this is the final computer, you'll boot and it will start running from address 0. Where do you want it to go after address 0? Well, you want it to go to address 1. Now, what am I going to use to change these dip switches? I really want a screwdriver. So what I want to do is program in 1, which is all zeros 1. Write that in. So in address location 0 of the memory, I actually have the data value 1. Now, when I clock the latch, which I can do with my single step button, it will take the data output of the memory chip, run it through the latch and represent it to the address input. So let's clock that. Now you can see that we're at address 1. Now, what will be the next address if we're at program location 1? Well, it'll be 2. So I need to feed a 2 in, write it into the chip, move on to the next location. So we're now at address 2. Now that address 2 was not counted. It was actually taken from the previous location, which was address 1, which had the data value 2. So in address 2, we need to put in the data value 3, write that into the chip. Now when I clock the latch, it will go to this address. So it goes to 3. In 3, I'll put in 4, write it in, and jump the latch, clock the latch. This is my clock signal effectively. So 4 will contain 5. Let's write that in. 5 will contain 6. That's 110. Right. Oh, I didn't write it, did I? Right. I think I've missed a thing. I'm going to have to go back to 0. That contains 1. 1 contains 2. Yeah, this display I've made, I'm actually using the central 8 bits. So I'm not using this end bit, so it's a little bit confusing. I should cover that up with something. Actually, I might be able to black that in with a pen, but I'll just leave it for the moment. So that's 2. 2 contains 3. 3 contains 4. 4 contains 5. 5 doesn't contain what I wanted, which was 6. I didn't write that in, did I? So that'll now move on to 6. 6 must contain 7. Let's write that in. And I go to position 7. Now, let's say, for example, that at location 7, I want to tell it to jump back to 0. So I can put in this unconditional jump branch back to address 0. So in 7, let's put in 0, write it in. And so now when I clock the latch, we'll go back to 0. Now, if I free run that, it counts from 0 to 7 and back to 0. It's running a bit fast. Let's see if I can slow that down. So we can see that going all the way up to 7 and back to 0. This is 1 ahead because it's providing the next address that we're going to clock into the latch. Right, I've used a black felt tip pen to black in the end 2 bits of this display, so it's a bit easier to read now. You can see that at address 1 we've got the data 2, at address 2 we've got data 3, at address 3 we've got data 4, and so on. So now that I've programmed this, it does actually count. Now let's say I want to do something like Arduino with a setup section and a loop section. Let's say I don't want address 7 to jump back to address 0. Let's say I want it to jump back to address 4, for example. So let's stop that, go to address 7 and program in a new jump. Instead of getting it to jump back right to the beginning of the program, let's get it to jump to 4. What's 4? 100? Yes, I think it is. So let's program that in. So now when it gets to address 7, it will jump back to address 4. And if I free run that, you can see that it's actually only counting from 4, 5, 6, 7. 4, 5, 6, 7. So when it gets to 7, it jumps back to 4. How do I get it to... So it's only executing the second part, the loop part. It's not executing setup. However, if I press clear, it will count from 0 all the way up to 7 and then jump back to 4. So we're doing setup and then loop. So this mechanism works very well for my setup and loop requirement. Now, of course, this does require a full programming of the address steps, because when the RAM is empty, it has no information on at each address location where to go next. So you have to program in to every address location some information on where you're going the next address when you jump to the next address, when you clock the clock and move on to the next program location. The other thing, of course, you'll notice is that now this RAM chip is entirely full of jump addresses for program flow. There's no actual space in this RAM chip for instructions, CPU instructions to actually do CPU actions. And that's why I've started to build here a second RAM chip. Now this will have its address lines, these 8 lines on the bottom left here, connected completely in parallel with these address lines. So the two RAMs will be addressed completely the same, but the data outputs here, I'll have another write switch block here, so you can write into this RAM as well as this RAM. This one will actually contain data which will be used as instructions for actually running the computer part, which I'll build down below here. So there'll be 2 RAM chips, both completely wired in parallel. So they'll just work as a sort of 16-bit RAM. 8 bits will provide addresses for the next instruction, and 8 bits will provide instructions to the CPU to carry out various tasks. Right, so I'm just going to program a longer sequence. On address 7, instead of jumping back to address 4, I'm going to jump to address 8. Let's program that in. Oh, that's interesting. Why did that do that? I don't know. Okay, so that's programmed in 8 for address 7. I can now move on to 8 and I'll program in 9. And I'll keep going with this until I've got a little section of counting so that this actually counts more than it was before, so you can sort of see it better. Right, I'm just at the end of a 4-bit sequence. This is E. I want E to contain F. Let's write that in and clock it, and that goes to F. Now I could have F jump back to, I don't know, let's say 4, or let's go 5. So 101. So F contains 5 and it jumps back to 5. So now it goes 5, 6, 7, 8, 9, A, B, C, D, E, F, and back to 5. So if I free run that, I'll speed that up a bit. It'll count up to F, jump back to 5, and run the program from 5. Now if I want to run the program from 0, I press my clear, which clears all the latch pins so that the latch contains 0, addresses the RAM with 0. It counts from 0, but then when it reaches F, it jumps back to 5, and then it counts from 5. Setup and loop. So, big thanks to John Measham for suggesting I look at this Laughton Electronics article, and a huge thanks, of course, to Jeff Laughton, who put this all together. Now, I have spoken to Jeff. This says at the bottom here, copyright Jeff Laughton. So I've asked him for permission to show this. I'm almost certainly going to be showing this again because there are some other very clever little tweaks in here, including a flag bit which can change another one of the address lines on the RAM. Now I'm going to use that for conditional jump, so that will be coming later. So what I need to do now is take these latch outputs which are driving the address inputs of this RAM and copy them over onto, using 8 wires, onto this RAM, wire this all up so that I can actually use, put another write switch in, wire this switch block up so that I can write into this RAM as well. So at each stage when you're programming this device, you'll write into this RAM the next address that you want to jump to, which in most cases will be the next address, but in some cases you'll jump back to create loops. And in this RAM, you're programming the actual instructions that make the computer do calculations. Now, of course, this is my computing section. It all needs to be rewired. It needs to go CMOS so that this spaghetti of wires is much easier to understand. The CMOS 574 and 541, I think it is, have inputs all along one edge and outputs all along the other, so that this processing element will be much more comprehensible. So there it is. The program counter has gone. This does still count, but you have to actually program the counting sequence in. Without a program counter, of course, I don't need to write to the program counter, and that was where I was having a real problem working out how I'd write to the program counter. This latch is being written to, of course, at every step. It's being clocked. Its input is the data outputs of this RAM. Its outputs go back into the address pins. Now, if you're thinking that doing this has made this more difficult to program, well, yes, it has, because for every address, you have to program 8 bits for the next address and also 8 bits for the actual instruction that the processing part of the computer will use to do the processing. So it does take more programming, but my design philosophy here is not about ease of programming. It's about minimum component count and making sure that all those components are available now from Chinese sellers to anyone who's watching this video. I don't want to buy anything from UK distribution outlets or anything like that. These have to be universally available parts, not expensive, freely available, no sort of difficult to obtain parts. And I also wanted to say something about this circuit here, where we're latching the data output from, well, in my case, a RAM into the latch and back into its address inputs. Now, you might think that there's a sort of built-in race condition here. You're clocking the data that's coming out of the RAM, but the instant you do that, you're presenting new data to the RAM's address inputs, and therefore its data outputs are going to instantaneously change. But they don't instantaneously change. When the rising edge of this clock signal goes high, this latch latches these 8 lines. There is a propagation delay even through this latch, so the Q outputs don't change for a few nanoseconds. That then goes around to the RAM. The RAM has an even longer propagation delay. They're actually quite slow, so the data outputs don't change for probably several tens of nanoseconds later. By then, of course, this clock event has occurred, and it's not going to be susceptible to any further changes on these data inputs until, of course, another rising clock edge occurs. So there's no race condition here. This actually works extremely reliably. So what I'll do now is I'll smarten all this wiring up so it's a bit less spaghetti-like. I'll wire up this second RAM chip, wire up this second switch block so we can put the actual program instructions in. And I'm still not at the stage where I can produce schematics for all of this stuff. I did do a full analysis of the clock and a schematic of that in a previous video. But as you can see, this stuff's all changing. I still haven't quite settled my mind on how this whole computer is going to work, so I won't be producing schematics until this is all decided upon. Anyway, for the moment, that's the changes I've made today. Cheerio.